Hello, once more. Welcome to topic 4.04 Half Life. Oh, yeah, it's not just a crazy video game, it's an actual property of radioactive materials. And interestingly enough, chemical reactions can also have a half life. Medication has a half life in the body. So you can apply this technique not just to radioactivity, but to anything that has a half life in its kinetics. The half life is the time it takes for half the radioactive isotope in a sample to undergo radioactive decay to a more stable isotope. So understand that when a radioactive isotope decays, it doesn't disappear. Remember last time? It turns into a daughter nuclide. And the half life is how long it takes for half of the nuclei to do this. Now, it's variable depending on what the radioactive isotope is. Different radioactive isotopes will release their radioactivity at different rates. The more stable a nucleus is, the slower it will reduce particles. And the more unstable a nucleus is, the faster it will release decay particles. So, isotopes of uranium can have a half life that measure into the billions of years. But isotopes of the elements that we created in particle accelerators, the really super heavy elements, have half lives that are far less than 1 second. So the duration of the half life is highly variable. But regardless of what the half life is, this is the decay curve followed by all radioactive isotopes. The only thing that will change is the time parameter. The longer the half life, well, the bigger these numbers are going to be. So let's look at strontium 90, which has a half life of just over 25 years. In the course of the first half life, half of the original sample will undergo decay. You'll go from having 10 grams to 4 grams. During an exact same amount of time, another half will decay. Not half of what we started with, but half of what we ended with the last time we had a half life. So we go from 5, well, it's a little less than 5, to about, 2.5. And then in the next half life, which is exactly the same duration of time, we go from having 2.5 to 1.25. And then in the exact same duration of time, we go from having 1.25 to 0.625. We can also look at this in terms of fractions. We started off with 100% of our sample. After one half life, we have 50% left. After a second half life, we have 25% left. After a third half life, we have 12.5% left. And after a fourth half life, we have 6.25% left. If we do it by fraction, we had 1 over 1 when we started, 1/2 after the first half life, 1/4 after the second half life, 1/8 after the third half life, and 1/16 after the fourth half life. The only thing that's going to differ is how long this takes, depending on what your isotope is. So, how do we find the half life of an isotope? Well, we take an isotope, we place it by a Geiger counter, and we count how many counts per minute the Geiger counter is recording. And when the amount of counts per minute is cut in half, then one half life has gone by. So, for example, if we're starting with 60 counts per minute, our first half life will go by when it hits 30 counts per minute. And then a second half life will go by once it hits 15 counts per minute. So going from 60 counts per minute to 15 counts per minute would be 2 half lives. Now, how long would one half life be? Well, if 2 half lives is 10 hours, then one half life would be 5 hours. Let's say we have a concentration of a different isotope in another sample, and it goes from 100% to 12.5% in 100 days. How many half-lives have gone by? Well, the first half-life would see us go from 100% to 50%. The second half-life would go from 50% to 25%. And then the third half-life would take us to 12.5%. So it takes 3 half-lives, 3 cutting in half of 100 to get to 12.5. 3 half-lives in 100 days. So how long would each half-life be? Well, you'd take that 100 days and you'd divide it by 3, and you'd get 33.3 days for each of those 3 half-lives. 33.3 days to go from 100% to 50%, 33.3 days to go from 50% to 25%, and then the final 33.3 days to go from 25% to 12.5%. Now, we can use half-life to make predictions as well. The number of half-lives is how much time has gone by divided by how long the half-life is. So, for example, let's say 100 days has gone by, and each half-life is 50 days. 100 divided by 50 means that 2 half-lives have gone by. Once you figure out how many half-lives have gone by, you'll either double your starting amount or cut your starting amount in half, depending on whether the question is asking you to go into the past or into the future. That sounds confusing, so let's look at some examples. I had a cat from 1998? Yes, 1998 until 2013. Mina was a Tonkinese, a sweet little girl. She lived to the age of 17 and a half. She was diagnosed when she was about 10 years old with hyperthyroidism, which is caused by a tiny tumor on the thyroid gland that overproduces thyroid hormone. And this can cause all kinds of metabolic problems. So there were a couple of ways we could take care of this. One, she could take medication, and the medication would keep the thyroid levels low. And that's what I opted to do. And she was on this medication, just 1 drop of it every morning in her food for the rest of her life. And she did very well on it. For a more permanent solution, which I probably would have opted for if she had been diagnosed with this earlier, was iodine 131 treatment. You see, the thyroid gland uses iodine to make its hormone, and it's the only part of the body that actually absorbs iodine. So if you inject radioactive iodine into the body, it will be absorbed by the thyroid gland, and it will kill the tumor that's producing the excess thyroid hormone. So she wouldn't need to take medication, and it's a pretty permanent solution. But the only problem was she would have to stay at the vet at our local facility, at least back then, was this place called Radio Cat down in White Plains, New York, until 1 half-life had passed. Now, how long is that? Well, if you take a look at reference table N, you'll notice that the half-life of iodine 131 is 8, up to the nearest day, 8 days. So that's more than a week. I'd have to leave her down there, and I don't like leaving her anywhere that long. I had to board her a couple of times, and I felt really guilty doing it. But that's not the worst part. Once I get her home, I wouldn't be able to cuddle with her because she's still too radioactive until 2 more half-lives had passed. And this would leave her with a safe level of radioactivity. So how many more days would I have to go without snuggling my little kitty? Well, since each half-life is 8 days, 2 half-lives would be 16 days. So the 1 half-life of 8 days and the 2 additional half-lives is 16 days. That is 24 days. That's the better part of a month I would have to go without snuggling my little girl cat. And this is a cat that would leap into my arms and lick my nose all the time, and you couldn't stop her from doing it. And if you closed the door, she'd stand at the door and just meow pathetically until you came to snuggle with her. So if I had sent her down to get the radiotherapy, I'd probably have cancer now, because I'm not going to say no to Mina kisses, except I have to because she died in 2013. Very sad. She was a very sweet girl. Anyway, more half-life problems. Well, let's say we have a sample of pure cobalt-60 and has a mass of 16 grams. How many grams of that sample will still be made of cobalt-60 in 21 years? The half-life is 5.271 years. Well, the first thing we do is we take that 21 years and we divide it by 5.271 years per half-life. Make sure you round to the nearest whole number. When you take a college course in this, you'll be actually able to do fractional half-lives. But for now, we're going to keep it simple. 21 years would be 4 half-lives, and it says how many will be left in 21 years, and that means 21 years from now. So that means 4 half-lives into the future. That means we're going to take that original mass of 16 grams and we're going to cut it in half 4 times. So, after the first half-life, we'll have gone from 16 to 8 grams. After the second half-life, we cut it from 8 to 4. After the third half-life, we cut it from 4 to 2. And after the fourth half-life, we're going to cut it in half from 2 to 1, which means that 21 years from now, that sample will only contain 1 gram of cobalt-60. Now, that doesn't mean that the sample has disappeared. It just means that the remaining 15 grams are made of decay particles and whatever isotope cobalt-60 decays into. A sample of potassium-42 gives a Geiger counter rate of 30 counts per minute. What would it have been 62 hours ago? And the half-life is 12.36 hours. So once again, we take the amount of time that has gone by, 62 hours, this should say hours, not years, and we divide it by 12.36 hours per half-life. 62 divided by 12.36 gives us 5 half-lives, and since it said, what would it have been 62 hours ago? Well, now we're going into the past, which means if we have 30 counts per minute now, 1 half-life ago, we would have had 60. The half-life before that, we would have had 120. The half-life before that, we would have had 240. The half-life before that, we would have had 480. And 5 half-lives ago, we would have had 960 counts per minute. And so we can make that prediction based on the half-life. Pretty cool, huh? Now, there's other practical uses for half-life. One of them is to figure out how old something is. For example, if we come across an archaeological dig and we want to find out how long that city has been there, we can look for some artifacts in that city. Wood is a really effective way to get this because wood contains a lot of carbon, and some of that carbon is carbon-14, which is radioactive. How do we make carbon-14? Well, it comes from the sun and from cosmic radiation. Cosmic radiation will actually cause nitrogen-14 to capture neutrons and turn into carbon-14. And carbon-14 is just one of 3 naturally occurring isotopes of carbon that are eaten by living organisms. So carbon-14 is found in all living organisms in a very specific amount. Now, once an animal or plant dies, it stops consuming carbon. And so the quantity of carbon-14 begins to go down, and it will change into nitrogen-14 at a very regular rate. So we can use the ratio of carbon-14 to nitrogen-14, or how much carbon-14 is left compared to how much you started with, to figure out how long this thing has been dead. Carbon-14 has a half-life of 5,715 years. So let's say we find an ancient wooden tool and it only has 25% of its original concentration of carbon-14. How old is this tool? Well, it would have originally had 100% of its concentration. After 1 half-life, it would have 50%. 25% comes after 2 half-lives. And since each half-life is 5,715 years long, we multiply the two together to get an age of 11,430 years. This is carbon dating, and it can be very accurate for things measuring anywhere from a few hundred years old to a couple tens of thousands of years old. You wouldn't want to use this to find the age of a rock containing carbon, because rocks formed much earlier, and after a period of, let's say, a couple 100,000 to a million years, the amount of carbon-14 that will be left after so many half-lives will be basically not measurable. So we wouldn't use carbon-14 to measure anything but once living organisms that lived within the last couple of tens of thousands of years. What if you want to find out how old a rock is? Well, you're going to need to find an element that's in that rock that's radioactive and has a half-life that's roughly on par with the age of the rock. This is where uranium comes in. Uranium has a half-life of roughly 4.5 billion years. Now, when we examine the oldest rocks on Earth, we find that they have a 1-to-1 ratio of uranium-238 to lead-206. Lead-206 is only formed from the decay of uranium-238, which means that half of the original uranium-238 has already undergone decay, 50-50. Since only one half-life has gone by, and that half-life is 4.5 billion years, that's how we are able to determine the age of the Earth as being 4.5 billion years old. And we've also found other radioactive isotopes with long half-lives that we've verified this age with. So now we have a good handle on how long at least the Earth's crust has been around. There are also medical uses of radioactive isotopes, although any isotopes you use should have very short half-lives and should be easily and quickly metabolized by the body. Basically, you pee them out so that you get rid of them. As you already seen, iodine-131 is used to treat hyperthyroidism. Here's the thyroid gland, right in your neck. And the iodine-131 will kill any tumor that happens to grow on the thyroid gland. Cobalt-60 is used for gamma knife treatment of cancer. They basically bolt your head into this helmet and they shoot targeted gamma rays at the tumor and it burns the tumor out. Each individual ray is not strong enough to harm your brain, but where they meet together, it's kind of like using a magnifying glass to focus the sun's rays to burn something. All right. If you aren't focused, it's not going to burn, but once all the rays are in focus, it can burn, and their precision is extremely accurate. How do you find this tumor to begin with? Well, tumors have abnormal clumping of blood cells. So you inject a radioactive isotope into the bloodstream, and then you can detect this using a radioscope. And you can actually, I can't see it here because I'm not a doctor, but you can detect abnormal clumping of cells in the brain. And then that would be the location of the brain tumor. And then you would take an MRI and you could actually verify and visualize the tumor and then use the information from the MRI to target your radioactive cobalt therapy. So cobalt-60 is used to treat the cancer. Technetium-99 is used to detect it. Additional uses would include the use of uranium and plutonium isotopes for fuel for nuclear power plants. This is where the fuel rods would go inside the reactor core. More about this at the end of the unit. Americium-241 is the source of ionizing radiation for smoke detectors. We have here a circuit. The battery is attached to these metal plates. Now, if you have no charged particles moving between them, then you don't have a circuit. Electricity only flows with a completed circuit, and alpha particles are charged and they complete the circuit. So as long as alpha particles are able to freely move between these plates, then electricity will be able to move, well, in a circuit. But smoke particles can stop alpha particles. And once the alpha particles are stopped by smoke, it will break this circuit and trigger an alarm. And this is how smoke detectors detect smoke. And that is all for this particular topic. When we come back next time, we're going to take a look not at natural radioactive decay, but artificial radioactive decay, also known as artificial transmutation. But until that time, I wish you well. And once again, bye.